Alright, so we've talked about this equation here, which relates our speed and the current speed, let's say initial speed, and then the acceleration and the displacement in the intervening time. So what I want to do is apply that to projectile motion. So you recall, well, let me see if this will actually write with me. Oh, because I got to get black. There we go. Projectile motion. There we go. Projectile motion. Alright, and the condition for projectile motion was the acceleration was constant with a magnitude of g. And so what we can get out of this then is well, let's look at a situation here where we have, say, this is our y-axis, this is our x-axis. So, you know, your typical projectile motion situation where gravity is going down in the negative y direction. So your acceleration vector is negative g times j hat. And you start at, say, some position r naught with a velocity v naught, and you move, through some trajectory to a position r1 with a velocity v1, and you want to relate these things together. So let's start with this equation up here. Well, first of all, let's look at this delta r term, which is going to equal your initial, your final position minus your initial position. But what it really boils down to is it's going to be your change in x times I hat plus your change in y times j hat plus your change in z times k hat. And so we have our acceleration now, we have our delta r. So this is actually very easy to evaluate this equation we've got. So v1 squared, which is our v squared here, we're taking v1 as our endpoint here, equals v naught squared plus 2 times this acceleration vector, negative g j hat, dotted with delta x I hat plus delta y j hat plus delta z k hat. Alright, so if we evaluate the dot product here, then it turns out that we get a very nice result here where the only component of this acceleration is in j. So when we take the dot product, this term, the delta x term, and the delta z term just vanish. And all that's left is this delta y term, because that's all that gets multiplied by j. So the result there is negative 2 times g, so it's g times delta y, and then we have the 2 and the negative 2g delta y. And this is for projectile motion. Motion with positive y going up. This equation holds. So this is surprising because it feels sort of non-intuitive in a way, but what it says is that if you have the speed of something at one point and then it changes its height in ballistic motion, you can find its speed at the other endpoint. And that's kind of it's a remarkable thing. When we get into energy later on, we're going to see if we say h is always positive y, so let's just say height above the ground, then this is another way to put it. And then this is nice because this kind of applies no matter what coordinate frame we choose. We might choose y to be vertical, we might choose z to be vertical, we might choose for some reason x to be vertical, but this just says the change in height, and we say an increase in height just means you're going up, you're going away from gravity. So we can say this h goes up, or say h positive goes up, positive h goes up. And this can apply to any coordinate frame we choose. This is a very powerful result, and it'll be useful later on when we get into kinetic energy and potential energy. In fact, if we multiply this by 1/2 m, you get literally the relationship between kinetic and potential energy. But we'll save that for a later time.